working today. Okay, great. So today's lecture is, so we have to finish something which we didn't finish last lecture, which was the example of the backpropagation. I think it's really key to go through that. And then we'll be talking about finally a task, something with natural language processing and something like deep learning, but not that deep, but still already like a building block of deep learning, which is very important, which is log linear models. So let's get started where we finished last time with backpropagation, because we were talking about minimizing a function, which could be any function, composed function of other functions, and each of these functions has to be differentiable. So this is our assumption, because eventually we're going to minimize the loss of a function. So the loss is kind of telling us like how well are we fitting the training data, and we want to make this loss as small as possible. And for this, we're using the gradient-based techniques as we were talking about. And for efficiently computing the gradient, we need to use something called backpropagation, which is utilizing the computational graph structure. And while traversing the graph, we're kind of applying the chain rule efficiently by storing the intermediate results and stuff like that. So this is a little bit of repetition what we talked about last time, and we're gonna have an example right here. So everybody's with me? Good. So here was the working example. I guess we started already. And this is very simple function, a plus b times b plus 1. And we need to compute the gradient with respect to a and b. So what is gradient again? What is a gradient? What is a gradient? Ooh, okay. What is a gradient? So okay, what is a gradient? Yes. Partial derivatives. Okay, it's in there. So this is something with partial derivatives. What exactly? So this would be partial derivatives. It's a vector of partial derivative with respect to all these kind of variables. Yeah, correct. So it would be partial derivative e with respect to a, and partial derivative of e again with respect to b, and this would be a vector. This is the gradient. Okay, so you should really know what a gradient is. This is very, 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 very important. Okay, so how can we compute the partial derivatives of this function? Any idea how to compute a partial derivative of this function? How to compute, for example, this? Yes?
You're doing the derivative with respect to a.
How about the other? How about b? Oh, this is constant, exactly. So you can do it per hand while treating, for example, this would be where you treat the other parameters or the other variables as constant, and the derivative would be per hand, basically using high school mathematics would be b plus 1, and this one with respect to b would be a plus 2b plus 1. If you don't know how to compute this, like go back and do a refresher on how to compute derivatives of single variables. So this is the trick. The thing is that, and we had this example last time, that if you want to compute a derivative of something more complicated than this per hand, it's kind of not tricky, but it's way too complicated and way too error prone. So you want to have a method to do it efficiently for any function. Okay, good. So this is the working example. So you could actually compute the partial derivatives. So the function for computing partial derivatives at any point b and any point any point a and b. But we want to build it into this computational graph because we're going to see how efficient it could be to compute any kind of function. So this will be the working example. Everybody with me? So the gradient. What is a gradient? It's a vector of partial derivatives. So what is a vector of partial derivatives, by the way? What is the gradient? Like, is there any meaning to that? Like geometric meaning? Yeah. So this is a direction because it's a vector. And what is this direction pointing to? Yes? This is the steepest ascent. So which means if I'm somewhere in the mountains on 2D landscape, the gradient would be pointing to the direction where the mountains go the highest, like the steepest kind of. So if I'm going to minimize a function, I have to go the other direction, downwards. Okay, good. So this is the gradient. So this is our function a plus b, b plus 1 again. And we're gonna add some intermediate variables, which I just arbitrarily choose here. So this is the output variable E. Then there will be two variables R and S. And I guess this is what we had in the exercise, actually, this function, right? Didn't we compute the value of this function in the exercise using the computational graph? I guess we might have. If not, well, I'll look it up. So yeah, we did. Yes, we did. This was the exercise last time. Okay, so this is gonna be the intermediate variables, and I choose the name arbitrarily here. So as you might see, this is my R, and this is my function now, S, or variable S. So far, so good? I'm just giving names. I'm just making it smaller. And these are very simple functions, like much simpler than this one. So I'm gonna build a computational graph, and this is what we did already in the exercise. I'm pretty sure we did this. So basically, the computational graph, each node here is a differentiable function which has some arguments, or children, as you might say. So for example, this E function is its arguments are R and S. This is the names I gave it. And these are another functions. For example, this one needs A and B are these nodes. Okay, so the leaves basically of this, it's DAG. And these leaves are input variables to me. And I want to make the gradient, so differentiate E with respect to A and with respect to B. Everybody's happy with this computational graph? So can you relate to that? Any questions? Okay, so this is important. So how to build a computational graph for any function? By decomposing into simple functions, which could be a plus function or a plus or a multiplication function. And we did this because I remember we programmed this sum node and product node. So this is it again. Okay, good. So here's again a refresher about the computational graph, but we basically covered everything already. Okay, leaves, variables, arrows, function composition. Okay, basically there's nothing new on this slide. But let's come back to the example. So we are starting with the output node here. And the first step we're going to do is to compute the partial derivative of E with respect to E. Why? Because this will be a recursive function, and you have to use the same rule over and over. So we need to compute E with respect to A and E with respect to B, and you were starting with the output node. And how does E change if E changes? This is the question. Just by 1. So the derivative is 1. So that's why we started with 1 here. Okay? I mean, this looks like ridiculous, and it's not a fraction, by the way. We said this, like this is not a fraction, this is a partial derivative. But we're going to be applying this rule over and over with different with different nodes in the variable. So we start with the last node, and it's going to be just 1. So it's not a special case in a way, but it's a starting point. So we treat it as this is 1, because then everything will kind of work together easily, smoothly. Okay, so any questions so far? How does the E, and E means here error or loss, how E does change when something changes? When E changes, how does E changes? Just by 1. Okay, good. So the next step then would be, we need for this function something which we call a local partial derivatives with respect to arguments. So for example, what is the partial derivative of E with respect to R? And what is the partial derivative of E with respect to S? Because these are the argument of the function, and we want to compute for each node the partial derivatives with respect to all these arguments for the function. So here the question is, what is the partial derivative of E with respect to S for this function f1? Well, this is a product. So partial derivative with respect to R is by treating S as a constant, which means it's going to be S, and the other way around. And I think this is what we had in the exercise as well. So you should know how to compute partial derivative of this function, and once you know it, you know how to compute how to have all these local partial derivatives. Any questions so far? Is it clear what we're doing? So for each node, I'm computing the global derivative with respect to the output of the whole graph, and I'm computing the partial derivatives with respect to the function's input in each node. So I call it local partial derivatives. And here, the arguments of this node are R and S, and I'm computing partial derivative of E with respect to R and with respect to S. So we're done here. So let's move to the next node here, which is gonna be S. So, oh no, not yet. Now we can traverse the graph down, and again, we are at another node, and we are interested what's the partial derivative of the global output with respect to this node. So partial derivative of E with respect to R. And now we are applying, what is this again? Why is this why there is a product? What is this? Yes? It's the chain rule, exactly. The chain rule. It's here actually, the chain rule. Chain rule, which says a composed function is, so derivative of a composed function is the product of the derivative of the outer function evaluated on the input, evaluated on the output of the inner function times derivative of the input inner function. Okay, so chain rule, recall this from last lecture. There's a reason why we were talking about this quite in detail. So now we know how to compute partial derivative of E with respect to R, which is using chain rule. Okay, do we have everything for computing this? So do we have E with respect to E? Oh yeah, we computed it up here. Awesome. Do we have partial derivative of E with respect to R? Of course, this is the partial local partial derivative from above. So now I can compute basically this value. And moving on. So remember again, we're computing the global derivative and we're computing the local derivative with respect to arguments for each node. So this is the only two operations we're doing, and we're traversing the graph and using chain rule. So let's move on to the, okay, any questions? Hi. So far, so good. So let's move on. Now, let's move to the next node, which is S. And again, we need to compute a partial derivative of the global output with respect to this node. So partial derivative E with respect to S. And again, we're going to apply the chain rule. So basically multiplying the global derivative up here with the local partial derivative from the parent node to this node. And that's how we end up with this partial derivative of the global output with respect to this node. Do you see the pattern already? So we're just traversing the graph and multiplying things together. So next, what do we need to compute? So now we need something like partial derivatives of this function with respect to its arguments. Okay, so we need to compute partial derivative of R with respect to A and partial derivative of R with respect to B. So what are those? So let's look at this function. So R is A plus B. Okay, so what is partial derivative of this function with respect to A? 1. Thank you. Yeah. So this is going to be 1. This is easy. It's already here on the slide. So the same here. So basically, for each simple function, we know how to compute the derivatives or the derivative computing function. So that's what we're doing. Okay, so we have these local derivatives. Does it make sense to go, oh, okay, well, there's no more to traverse because these are numbers. These are not functions anymore. So we don't have to traverse into these nodes. So there's one more node remaining, and this is, oh, actually not. What is the global out? So what is the partial derivative of E with respect to A? Well, again, we're using the chain rule here. So we're using the global derivative with respect to its parent, which is coming from here. And we're using the local partial derivative of the parent with respect to this node, which is partial derivative of R with respect to A. So basically this kind of depiction of this edge here, and multiplying these two together to get partial derivative of E with respect to A. What is this? What is partial derivative of A with respect to E with respect to A? What is this? Why this is interesting? Yes? If you change A, how much the output will change? And at the same time, this is one item from the gradient, like because we are interested in getting the gradient of the whole function, and the gradient whole function is the partial derivative of E with respect to all these inputs, which is A and B, and we already computed this one. So this is how we recursively basically computed what we wanted. using chain rule and doing traverse on the computational graph. So this is why it's kind of interesting. Okay, so let's move on here. We want to compute the same for B. But before going, so we need a local partial derivative for S function. So there is only one argument. So what is partial derivative of S with respect to B? Well, what is the S function? B plus 1. So the partial derivative of that with respect to B is going to be a constant, 1. Okay, so we know this. So this is 1. And then we can move to the last node in the graph, which is what is a partial derivative of E with respect to B? So with respect to this node, so the global kind of output, how much it changed. Now we're using something we discussed last week, I guess, 2 weeks ago, multivariate chain rule. So because we have two parents, we need to sum up all these incoming or all these parent global derivatives and multiply them together. So this is multivariable chain rule. We're going to take this parents times this local derivative plus this parent times this local derivative and sum up together. So this is the rule we know from calculus. And voila, we end up with partial derivative of E with respect to B. So basically, these are the only operations I'm using on the traversing the graph. First, output a global, sort of global output or global gradient. So with respect to the overall output, this is what I'm interested in. How much the output change if I change something deep in my network at the beginning. And then by traversing and using chain rule, I'm gonna compute basically everything I need to end up with the gradient. We just made it. We have it here. Yes. We computed it for, and now, I mean, these are all these gradients. This is like how to compute a gradient. But at the end of the day, a gradient is a bunch of numbers. Like if you evaluate a gradient at point A and B, you will get two numbers, real numbers. And these numbers is the vector pointing to the steepest ascent. So these are numbers. But we're now dealing with, so this is like kind of the ambiguous thing of what is a gradient? Is it it's a vector of real numbers, but also we understand it sometimes like as the function which computes this gradient value. So maybe we should call it gradient value, and the gradient is a function for computing the value. But it's really confusing. Also like in the literature, if you see that. So gradient could mean many things, but one of these two things basically. So the gradient is the vector or the function how to compute a vector. Okay, so we have a very complicated thing for computing gradient, because you could do it per hand. But the trick is, all these operations, I mean, however now you build a graph, you will use the same operations on any graph. And as long as you can compute these things, the global output with respect to this node and local partial derivatives with respect to arguments, you can compute any gradient for any differentiable function, which is called composed function. Okay, do you see why is it somehow interesting? Because you don't have to do anything per hand on the huge functions. You just need to know how to compute derivatives or partial derivatives of small functions, like a product, sum, what else? Logarithm, sigmoid. But these are simple. And you just take them together and use chain rule wisely. Okay? Any questions? I strongly recommend you to go through this example by your own again and try to really understand it, like that you really know what is going on. Once you see it through, it's like matrix. So wow, okay, this is just a computational graph. Getting there maybe takes a while. Okay, so I try my best, but you know, we did something in the exercise already to try to program this. So go back, look in the exercise how we basically build this graph, how these gradients propagate. Try to evaluate a couple of gradients, and then you will see the light at the end of the tunnel. Okay, so this is it. So basically, for each generic node in computational graph, we have some arguments. I call them A1, A2, AN. And so these are basically inputs to the nodes. Could be numbers, could be other functions. We don't care. So as long as this produces some value, like real value. And it could have multiple, let's say, parents. So there could be other functions. And typically somewhere here, there will be some like output node, which is typically a real number. Everything just go into there and computes a number. And we want to make this number as small as possible. So we use the backpropagation to compute the gradient with respect to all these inputs here. And once we Once we get this, we know the gradient, we do something else, which we'll talking about later. But this is how to compute the gradient of any function. And these are the two things that are crucial in there. So we are talking about this, like the chain rule for multiple variables, basically. And each node must implement basically these two operations: how to compute the output. So each function must know how to get the output of the function, how to compute a value, and then how to compute partial derivatives with respect to the parameters. So for example, if I have this function s, I have 4 parameters a, b, c, d. So I need to understand how to compute these partial derivatives. If I can do this, I can stack it into my computational graph and do magic. Well, not magic, but just... I think we had it last week maybe for this logarithm node. I mean, we kind of implemented a logarithm node which can compute a value. Was it logarithm? I guess so. And then what would be the derivative of logarithm? We just take it in, and then you can do the computations with that. So basically, it's like a modular framework in a way. Once you have a function which kind of adheres to this interface, so to say. So there's two functions you need to implement. Then you can stack it in your computational graph. So it could be, I don't know, could this be multiplication of vectors and matrices? Yeah, well, then maybe it's not a real valued function. It would be a function which outputs a vector. So it's maybe a little bit more complicated, but not that much. But basically, these are two things we need to implement. Okay, any questions? Are you with me? Good. Okay, that's great. So that was backpropagation. Well, why is it called backpropagation? So basically, first, it depends how you implement it. So you can do one thing, which means first, so-called forward computation. You compute all nodes output. So if we go back to the graph, we just say, okay, so let's take these inputs, and then so A and B will be some actual numbers, like 2 and, I don't know, 2.1. And then you want to know what is the output of that for each parent node. So this will be, what is R? A plus B. So it would be 4.1, and this will be 2.1 plus 1, 3.1, and all this stuff. So basically compute the output first. That's why it's called forward. And then the backward computation, the backpropagation, compute the overall function's partial derivative with respect to each node. This is what we are going through, like from the top. What is the partial derivative of this node with respect to the global node? What is partial derivative of this and this and this and this? And that's how we end up with the partial derivatives. So there's two passes. How you implement it, basically, it depends on you. So you may basically do just the traverse, like recursive traverse in the graph, and just call the partial derivatives. And the partial derivatives know that they need the value of the children node, so they can call it in the recursion as well. So it's a matter of implementation. If you do it in like first neural networks implementations were in MATLAB, where you have like a very clear. So there was not really like computational graph as far as I remember. And you had to do like a manual kind of computation and know what comes first, what comes next, and stuff like that. So, but if you do it like a computational graph where you know exactly what's a parent and what's a child, then you can just call a recursion on the graph. Okay, good. So recapitulation. We can express any arbitrarily complicated function. Now, I mean, we're talking now about real functions, so real value functions, as a computational graph. Okay, this is nice. Like, maybe many of you didn't know that before, but you can compose a function as a graph. And then for computing gradient at the concrete point of the input, we run the forward and backprop. And the thing is, one trick is that we need to implement caching. So what is caching in computer science programming? What's cache for? Yeah. Store something for later. Why do you typically cache? So what do you cache typically? Something which is to be accessed later again and hard to compute. Yeah. You use it multiple times. Exactly. You don't want to recompute the same thing over and over. So this is exactly what is in backprop, because if you do the recursion and you're calling again the same values from the output from the nodes deep in the network, you would compute it again. But these won't change. So you just store them in the cache. What's the trick with using cache? Where's the catch if you use cache? Generally, in computer science, if there's a cache, there's a problem. Why? If you don't have any memory issues, like let's say you have infinite memory, you have like external database. You need to keep the cache fresh. In other terms, you need to know when you have to invalidate the cache or delete the cache or purge the cache, empty. If you forget to empty your cache, then you have problems like unexpected behavior because you're running a function saying like, why isn't it changing as as I need to change it right now? I change all these variables, so what's going on? And somewhere in your network you forgot, or in your system you forgot to purge a cache. And then wow, okay, that's tricky. So I think like many kind of real world issues in computer science in general is because somebody just forget about a cache or caching something which wasn't invalidated or should have been invalidated. Okay, so this is the cache, and that's what we're doing here in this network. And I think if we didn't implement it yet in the exercise, we will have to implement it. And there was this issue. I think there was this last task of the previous exercise, where people are saying it runs. You were saying it runs forever. It's a bug. And then I look into this, and it'll feature basically, because we were stacking a couple of things together, and because of that there was no cache, it recomputed all the values again and again and again, and it ran for 10 minutes or so. So it felt like it's crashing your laptop. It didn't, sorry. But it was a feature. Once you implement the cache in computing the output of the node, and it's just 6 calls and you're done. So this is why it's important, caching for backpropagation. Caching is a key for backpropagation. All right, takeaways. We can do it. Let's give it like that. We can do this. So we have a tool for efficient implementation of gradient for any function. This is great, as long as it's differentiable and we can build a graph. Awesome. Now, let's move to the application. So how to use it? This is a cut from the previous one. So we have a function, we know how to minimize it, and now what can we do about it? Text classification. So we want to solve a task, and the task is very simple. If you remember lecture 1, the IMDb dataset, so the internet movie database dataset, review positive or negative. So basically 25,000 positive examples, 25,000 negative examples, and these are some reviews. And the standard task is binary sentiment classification to positive and negative. So we should learn a simple yet powerful supervised machine learning model, which is known as logistic regression or maximum entropy classifier. And in a way, it's a single layer neural network. So there's no hidden layer, but you can treat it as a neural network because you can call these things neurons, if you will. Essential, and this is essential important building block for some deeper neural networks. So this is like a basic building block is a logistic regression. And you know it maybe from statistical learning theory. It's a well-known, well-studied thing. Logistic regression is like the bread and butter of any statistical learning or machine learning. But we can implement it from scratch using our network. This is kind of cool. I mean, we're using scikit-learn or other libraries, so it's implemented everywhere. But we can build it from scratch very easily. So, what is now we have to describe our function. So, okay, because our problem of learning, as we discussed, is so we have a function which maps input to the output, and function could be anything. But we're going to stick now for a sort of very limited function, which has some parameters and some form. And the parameters are here W and B. They have a meaning, which I'll tell you later. Well, okay, matrix W and vector B. So these are called, I guess, weights, and this is called a bias. So weight or weights, and B is a bias. And if you look at this form of this function, so what is this? It's a vector, this is a matrix, and this is a vector. It looks like a line. So if you remember a line, like y equals A times X plus B, this was a line. Now we're moving this to multiple dimensions, so this will be a vector, and this will not be a vector or a number, it will be a matrix. Okay, so we're multiplying inputs by matrix and adding some other vector. So these are parameters. So the W and B are parameters, and we use this symbol. What was this name again? This ugly little thing. Yeah, theta. Yeah, theta. So we're using theta for parameters, and this x is the input. And the function is like from some input dimensionality to the output dimensionality. And of course, we need to find such parameters that the function does what we want. So predicts the desired output on the input, for example, by learning this from the training data. But let me a little bit maybe, what is next slide? Yeah, okay. Just this kind of function, what that is. So what happens if you multiply a vector by a matrix? What you're doing? What is multiplication of a vector by a matrix? So first, what you're getting out of this? If you have a vector and multiply by matrix, what could be the output? Could be another vector, could be also a scalar. Could or not?
It's like a one row matrix.
It could be a scalar. Okay, so it could be you can project a vector into another vector of dimensionality of 1 to n. So it could be scalar. Okay, that's great. So you have a vector. What does it mean? What does it mean? What is a multiplication by a matrix? Does it have a geometric meaning? And if I'm asking like that, maybe it does. So what do you think? You're close. So it's transforming a vector into something else. 3D, yeah, okay. 3D what? Yeah, X, Y, Z, okay. And then you're onto something. You're onto something. You're getting the intuition. I see you. Let me just, okay. So it's like in linear algebra, you would transform into another base. It means you will transform into another vector space, which has different base. But like geometric interpretation of that could be. So let me give you an example. I ask you an example, and maybe you have a solution for that. So if I want to transform something from 3 dimensions into 2 dimensions using a vector by matrix multiplication, what I'm doing? Exactly, I'm projecting into some other space. And the projection is linear. So for example, what does it mean? If I have an object in 3D and I project it, for example, on 2D on a wall, this is a projection. I multiply by matrix. So, and depending on the projection matrix, I can like make it smaller, bigger, rotate, translate. But what will happen? What can never happen in this projection? What I cannot do in this linear projection. So I can do many different kind of rotations, maybe. I think I can do rotation. Yeah, I guess so. I can do rotation, I can do squeezing, making bigger, smaller, shrinking, but there is one thing I cannot do. I cannot twist it, I cannot fold it. Lines will be lines or dots. If you project into like, in a bad way, it will be a dot but lines, linear relationship in the original space will be a linear relationship in the target space. This is why it's called linear algebra, in a way. It's a linear projection. You cannot, if I have a 3D object here and I project it on a wall, it won't be like twisted or squeezed or something like that. The lines will be lines. Could be smaller, bigger, whatever, rotated, translated. So everything which is linear in one space will be linear in the other space. Does it make sense? This is the insight I'm using for linear projection. Like, yeah, sure, you can make it bigger, whatever, rotate, but yeah. Say again? Well, it depends what's in this matrix. Like however you design the projection matrix, you can project things like you can project into smaller space if the matrix has less rows. You can have more rows to project to larger space, but the linear relationship will be still there. So this is an important learning from the linear projection. Linear function is basically linear relationship will stay linear relationships in the target space. And then this like B is a bias, so I shift it somehow. That's it. I'm just adding a vector and I'll move it in the target space. Okay, so everybody with me on that? This is an advantage and disadvantage at the same time. Advantage because it's fast and blah, blah, blah. Disadvantage, you cannot fold it or squeeze it or shrink it or kind of do the stuff in the new space. It's just linear projection. Okay, so this is the function we're going to use. So it's something like linear function, but in multiple dimensions. And the input dimensionality could be different from the output dimensionality. By the way, I put a couple of slides on examples multiplying vectors and matrices to the appendix of the slide. So if you want to refresh that, just scroll to the bottom of the slides, and there's some examples of how to multiply vectors and matrices, which you should know, but just as a refresher. Okay, let's go. So the binary classification, again, is a function. We have, basically our function is going to be even simpler. So the output space will be a scalar in this case. So because I'm interested in, I have two categories, positive and negative. So I'm going to start with the labels. So what's the input? X, it's an H language text. It's going to be a little bit tricky. The output are two numbers, or not two categories, positive and negative. And I'm just going to arbitrarily map them to 0 and 1. This is arbitrary decision. I'm saying, well, this is 0 and 1 is positive and 0 is negative. It could be the other way around. It could be anything else. But this is just convenient. Let's put it like that. So you can turn any binary task into 0 and 1. And you have to know the meaning of these 0s and 1s. Okay, so everybody, yes? So, okay. Because you asked for this. So this is an example. So we're using row vectors. Not in physics, we're using row vectors. And this is d in dimensionality, so then the matrix d in times d out. So basically number of columns will be the output dimension, and here I have to match, so this will be, this multiplied together will be what? 2 times, yeah, well, it will be two numbers. Right, 3 times 3, so this, and this times this column, so it'll be two numbers. I add two numbers and I get the output dimension. So basically this kind of row, the way of multiplying first vector times matrix is easy because then you see like what's coming in must be the first dimension of the matrix, and this is the output dimension of the matrix, which is matching the output. Yes? Yeah, so we're making it even simpler, and now it answers your question, because yes, of course, because if the output should be one dimension, this has to be, this has to be one, a vector of basically, this has to be a vector of the same dimension as x, like one column matrix. Yeah. Okay. So now the question, so we know the labels. Now how to get a natural language text into that? That's kind of tricky because this is a function. So how you turn language into numbers? So how can we turn a language into, so what do we want? We want a function which is, this is the input, so it should be vector. That's what we need for our function to work. And this is what we have. This is the real example from IMDb. So one of my favorite movies, The Shawshank Redemption, is a modern day classic, and it tells the stories of two inmates who, so everybody knows the movie and everybody knows it's a great movie. Well, you may disagree, that's fine. But this is the review. How do I turn this into vector of numbers? Okay, tokenized. This is interesting. So yeah. Into what? Yeah, you can tokenize it into numbers. Yes? You can use ASCII and encode every character. That's possible as well. Yes. You're onto something. So we will tokenize it or split it into words. And what is a word? I don't know. Do you have an answer what a word is? We have linguists in the room. Something like that. Okay, something like that. So we take very simplistic definition. Words are sequences of letters, and they're separated by white spaces. But then the question is like, okay, is dog a word and dog question mark? And there's no white space, so these will be different words. So maybe we separated in white space and maybe some punctuation. So it's getting a little bit arbitrary, and we're kind of sloppy in this. But why not? Because it works most of the time. And we call this process tokenization. So it splits the words into something called not words, but tokens. So tokens is some sort of a chunk of text. And based on some white space punctuation in English, it's very easy. So the job of tokenizers is quite simple. You just chunk it. In some other languages, sometimes there's no white space. I don't speak any Hebrew or Arabic, but I kind of believe this is true. But in Chinese, for example, you have no white spaces. So if you build a tokenizer in Chinese, you have to do it somehow differently. Yes?
Is it same like encoding thing, like encode?
No, you just split the text. You just say, oh, this is a token, this is a token, this is a token, this is a token, this is a token. So you turn a sequence of characters into a sequence of tokens, and the tokens somehow correspond to words. Yeah. Yes. So, and the thing is, again, the tokens like cat and cat with capital, they have the same meaning, but are they the same word? Who knows? So is New York one word or two words? And all these things. So, this is kind of arbitrary and tricky and depends really on the application and what we're using. Typically, we're gonna just tokenize everything by white space and let the model handle everything. Sometimes you can take arbitrary decisions. The output of the tokenizer is a token and the meaning, but we use words, something which you can find in a vocabulary, so in the dictionary. If you open, I don't know, like Duden, there's words. If I tokenize a text, I have tokens because maybe there's some flexion in the words or some morphology and stuff like that. So we are not pedantic about using this term word, because the story is more complex than that. So words, tokens. We're gonna tokenize something. We're gonna split it into tokens. So what we're gonna do is we first need something called vocabulary. So we can take some training data and tokenize that, and it gives us a set of all different kind of words which happen to be in our training data. So typically, the size could be, I don't know, something like 20,000 to 100,000 words could be in our vocabulary, roughly. And you can build your vocabulary. So what's going to be the distribution of the vocabulary? Like, what do you think? How are words distributed in language? How are words distributed in language? Like, what's the frequency of different words? Is there something we can tell about it? Zipf law, exactly. Nice. It's a Zipf's law, something like that. I guess it's probably written like that. Zipf's law. What does it say? Roughly.
In terms of its frequency is like inversely proportional to something.
Yeah, to something. I don't know it either, but I know like there's some sort of very skewed distribution. So you have something like most words, and I think it's something with length as well. No, it doesn't. Well, maybe the length in some languages, but some words are very frequent and are very, 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 and then you have a long tail of very rare words in a way. So, and maybe some words just are not used at all. I don't think this is Zipf's law, to be honest, but it's just a distribution of any words. It's very skewed. So you have the very typical words used all the time, all the prepositions, very easy words, and then you have words which you see just once in a lifetime, for example. But the Zipf's law I don't actually remember, but there's a Zipf's law which is saying something similar. So it's a like logarithmic or 1 over n, something like that, right? To its rank. Okay, yeah. So the rank is meaning the frequency, basically. Okay. So I wasn't too much off, but don't take it for. I haven't changed the flow for this lecture, so I don't remember exactly. Anyway, so we have this. We have very many frequent words, and then we have some words which are just infrequent, so just appears maybe once or two times in the training data. So we might cut them off and say like, okay, this is going to be our vocabulary, and this could be like 100,000 words. And then each word from this set, so this is going to be a set basically, each word has a unique fixed index. I can sort them by alphabetically. I can just leave them by sort them by frequency. It's my decision. But then I have a, each word has a index. So if I have 3,000 words, this could be these words and their indices. Okay, so far so good. I build my vocabulary from my training data. I get it from the internet, whatever. And then if I want to represent a sentence or document, I take each word at position and take its vector from the vocabulary, where I use 1 for the position of the word in vocabulary, and zeros will be otherwise. That's why it's called one-hot encoding, one-hot vector. So here's an example. It's better. The formula is kind of way too well. It's just a simple formula for. Simple procedure for with unsimple formula. But let's have a sentence. A cat set. So these are 3 tokens. A cat set, and I have this vocabulary. So where I know that A is at position 1, cat is at position 852, and set is somewhere else. So I'm going to look up word A in the vocabulary. So which is and I'm going to assign this to position. Sorry, I'm going to assign it value 1. So at position 1, because there was A, I put it 1, and the rest will be zeros. Then the same for cat, which is everything is zeros except for the position where cat is in my vocabulary. So it's 852. So there will be 1, and the rest will be 0. And the same for set. Maybe it was at position 2000 something something. So basically, I'm saying each of those have what these vectors have the same. They have the same size, exactly. They have the same length, and all of them are mostly zeros, except for just one position. This is the position of the word in vocabulary. So this is one-hot encoding. Okay, everybody's with me? So this is how you look up a one-hot vector for each word. And then, how do you represent the whole sentence? You just take the average. You just sum them up and divide by the number of words. It's very stupid. It ignores very many things from language. And it works for very many surprising cases like text classification. So why is it called back of words? What do you think? Why is it back of words? Yeah. Yeah. You throw everything in the back and you don't care what comes first and second and third. And you take the average. Yeah. So what are well, do I have an example of okay, here's an example of the same thing. So just very clearly, this will be the resulting representation of the input. So sum up these 3 vectors and divide by 3, so it will be this vector. So this is the small simple representation of a document as a vector of numbers. I have a vector of numbers. It has a dimensionality. What's the dimensionality of this vector? Say again? Yeah, 3000, exactly. So the size is 3000. Which is the size of my vocabulary. Okay, so I have 3000 vector. And now, no matter how long my sequence is or sentence is, everything will be crammed into 3000 size vector, right? Because if I have a cat set on the mat, which is somehow very popular sentence in linguistics for some reason, I don't know why. So a cat set on the mat, I can do the same thing, same procedure, add more cat set on the and so on, and do the average, and everything will be again in the same kind of same space, 3000 dimension space. Okay, sounds great. So why is this good? Well, everything will fit into our framework, if you will. Why is it bad? Why is back of words bad? Well, where will it break? Well, like what won't work in back of words? Why is it bad? Yeah. Yeah, because the order of words matters. Example? Give me an example. Which phenomena will just won't work? Okay, for example, negation. That will be the issue because you will lose this information in negation. If you have negation to something in your sentence, it will be like lost to which. Or Mary landed John a bunch of cash. If you throw it in the back, you don't know whether Mary landed John a bunch of cash or John landed Mary a bunch of cash. Or yeah, cat and set have different positions in the vocabulary. So here's my vocabulary. So here's a cat at position of my vocabulary 822, and somewhere here would be set at position 200172 or something like that. Okay, so this is my vocabulary. It's basically a list of words indexed by its position. So then I know each word is unique to some position. So I can map words to indices, to numbers. So basically I map the sentence into 852 2179, and then turn this into this vector by looking up, well, basically turning this into one hot vectors and then to the average. Okay, cool. So back of words, good. We might have an issue if there's unknown words, because words in language are very unevenly distributed, and there's this large tail of rare words. So we might be, we have a vocabulary, and then in our training data or test data, whatever, we have words which we don't have in the vocabulary. So how do you treat this? So typically, you can ignore the word, or you just replace it with something which we have a special token, UNK, like unknown. So we put it a special position unknown and extend the vocabulary by just one unknown token. And whatever comes then, you will, and you haven't seen here, if you don't see it here, you just say, oh, it's an unknown token, and just map it to unknown. So this is like an ad hoc solution for unseen words. A heck, that works. In machine translation, how would you translate the unknown word? Oh, this is interesting. Shall we go there? Why not? So if you translate from one language to another, you have vocabulary, and there's an unknown word. How do you translate the unknown word? Just leave it as it is. Just copy it from one language to another. Exactly. But there could be a better solution, because the unknown word, I mean, maybe there's some linguistic properties like morphology or tenses in the words which you haven't seen, and you want to translate it as well. So there's better ways how to handle unknown words, or actually how to get rid of unknown words altogether. And this is not splitting into tokens, but splitting into subword units. Right? So we are splitting into tokens by white spaces, but maybe the words are just too large, not too large, too long, but maybe we can, what would be the maximum could be splitting everything into characters, as you suggested. Like we can have characters, but then if you want to represent a sentence like the cat sat on a mat as a bunch of characters, then you completely lose any meaning, because you would have like just basically a distribution over alphabet, which is kind of, is it really a sentence? So the words have meaning. They're discrete, they have meaning, and we discussed it in the first lecture, like why words are interesting. But we can do something in between, maybe split a word into subword units. And one of the examples is byte pair encoding. So we take the words in the corpus, and first we split them into characters. This is our initial vocabulary V. Okay, so everything now in the vocabulary we have all characters from the alphabet. Then we take the most frequent pair of characters and merge it together and add it to the vocabulary, and we're gonna repeat this while we can, or whatever, when we say number of times, and then we say, okay, we just reached the size of vocabulary, we're good. So when we do this over a large corpora with multiple languages, maybe, this byte pair encoding, this actually prevents out of vocabulary, because we can represent every word in the language. In the worst case, it will be a bunch of characters, but maybe it will be a bunch of subtokens. So there's an example in the next slide, which we'll go through, and will be pretty clear. So we have this toy corpus. So this fat cat, which with the head is in the cave of the thin bat. So these underscores are white spaces. Now we'll find the most frequent pair of characters, which will be, if you do the screening here, will be T and H. So it's 6 times. So we want to merge them into a single token here, TH, TH, and so on. So we'll get this new corpus. And of course, TH is already in the vocabulary, because T and H are, excuse me, we add TH to the vocabulary also. Then again, we're gonna look into the most frequent pair of things, which is gonna be A and T. Okay, so 4 times. So again, we merge A and T here, here, and so on. And the next step, again, okay, now what is the most frequent here is TH and E. So we're gonna merge TH and E and here and add it to the vocabulary. So I'm always looking for the most frequent pair of consecutive tokens and add them to the vocabulary. So after this step, my vocabulary is all these characters, of course, this is what I start with. And then some bigrams in a way, and some trigrams. And some trigrams actually look like words, of course, because they are so frequent that actually they relate to words. They don't necessarily have to be words, but these are subword units that are frequent in the training data. So using this, for example, you can say, well, my vocabulary size could be something like 30,000, and you run this on your corpus, you will end up with vocabulary where you will end up with very many words, which are actual words, and very many sort of subword units, which are also somehow meaningful. For example, ing, like the, how's it, gerundium in English? Yeah, ing form. So you will have ing. And then why is it good? Because then if you tokenize using this vocabulary, then you might tokenize the full word if it's in your vocabulary, or you can tokenize 2 parts of the word. For example, swim. No, swimming is bad. Give me an example with ing. Eating. So eat and ing. If eating is not in your vocabulary, maybe there's a chance that eat and ing is in your vocabulary. So we'll split it into 2 meaningful units, eat-ing, which bears some meaning. Okay? Yes. So white spaces are tricky, and then that's why byte pair encoding or BP is there's better ways to do white spaces, and this is sentence piece. So, and actually here's the sentence piece is that how do you do that? Sentence piece escape the white spaces by this underscore first, and then tokenizes the input into an arbitrary subword sequence. So in sentence piece, you would basically prevent losing the white spaces in your data. So which means sentence piece, if you have hello world in sentence piece, it's similar like BPE, but you have these white spaces, you would be able to tokenize into tokens like hello world. So for example, this is one. So each of those corresponds to one word in your vocabulary, so to say, or in its vocabulary of subword units. So you can split it into tokens, and you can reconstruct exactly the original sentence, including the white spaces. So this is a lossless tokenization, and that's why it's all, I guess nowadays this is like the mostly used tokenization in NLP, like sentence piece, because you're not losing any white spaces. You can tokenize and reconstruct back the original text. Okay? Does it answer your question? Any other questions here? So you build it basically from, you build it similar way as byte pair encoding, but in byte pair encoding what did we do here? Well, nothing special. It's basically the same procedure. So you build it up by looking at the frequencies from the words. And there are different implementations of the tokenizers. So just a warning, whatever you use in your, I don't know, like a tokenizer in your framework for any experiments and stuff like that, tokenization is crucial. So you should know which kind of library you're using, how was the tokenizer trained, what exactly sentence piece implementation is, because these are tiny little details, but it will somehow impact whatever, if you generate a text from the model, if you do translation. So tokenization is kind of still tricky. There are methods for actually completely removing tokenization and just work on characters or even on bytes. But working just with bytes is tricky for many different reasons, such as, the length of the input is kind of limited if you work with just bytes, characters. But if you have something longer, like subwords or words, you can cram in much larger context. But we're kind of getting too much in advance because this will be important for transform models. For now, we just want to tokenize a text, but I just wanted to say like tokenization by white space is okay for easy tasks, but there's much advanced tokenizers in subword units which are actually used in contemporary NLP. Okay? Good. Wow. Now, so the goal was we want to transform text into vector. And again, we had a smoothie and we had a solution back of words. So, okay, back of words works. I mean, the size of that will be size of vocabulary. There are some disadvantages, advantages. Could be back of subword units. It's fine as well. So whatever, some sort of tokenization. But basically, each document could be a vector. So what we're going to do right now. Any questions? So we have a label binary, which will be 0 or 1, which is great. And we have a text, and we can turn any text into vector. Okay, we're good. So let's build a model. So again, our function was this linear function input times v, which is a linear projection, and plus b. So this will be our building block, the linear function. So how exactly it works? Oh, by the way, this is also, if you multiply two vectors like that, this is a dot product. So in one-dimensional, excuse me, for multiplying two vectors, you can multiply vector by a column matrix, which is linear projection, and you can also pretend it's a dot product, which is the same thing. If you don't know what the dot product is, just scroll to the appendix. I think there's an example of that. But basically, multiplying a vector by matrix and adding some bias here, which is a real number. How exactly that works? You just multiply each element with each element. So basically, vector by vector multiplication. So we know how to compute the output. Okay, so we know how to get from input to the output, and also because we're gonna, plug it into our computational graph, we need to know how to compute the derivatives of this function. And this is pretty easy in this case. So what are the derivatives with respect to parameters w and b? So the w's there's actual multiple w's, w1, w2, w up until w size of the input. And there's one bias parameter. So this is easy. What is the derivative of this function with respect to b? So everything else is constant, so the derivative will be 0, and derivative of b with respect to b will be 1. Okay. Partial derivative, very easy done. Does it make sense? Okay. So what is the derivative of this function with respect to, for example, w1? Well, everything else is constant, so it will be 0. And derivative of this function with respect to w1 will be x1. Yeah, okay, easy. Then the derivative of of w2 with respect to, derivative of this function with respect to w2 will be x2, because the rest, everything else will be constant. So basically, here's how we get this generic formula for any parameter here will be its corresponding x. Okay, does it make sense how we get there? Just use this, try the partial derivatives here per hand, and you will see the pattern. I mean, there's nothing magical about it. Okay, but it's actually pretty convenient. So we know how to compute the partial derivatives of this function. Awesome. So this means that this linear function, which takes d in inputs as parameters and some d in numbers as the x, can be plugged into our computational graph. We can compute the output, and we can compute the derivatives of that. So we can minimize this function if we want. We can take a gradient of this function, and we can use it for minimization any other function. And that's what we're going to do. So, but now here's the thing. So we have this function from some input dimension. So for example, again, so what could be this if we have this vocabulary we were talking before, like 3000. So input dimensionality will be again 3000, right? Because we have 3000 parameters. Oh, 3001. No, that's, sorry, excuse me, 3000 input and 1 dimension output. And what will be the number of parameters? What is this going to be? How many parameters now we have now? Yes. 3001. Say again?
3000 W's and 1 B.
3000 W's and 1 B. So it's going to be 3001 parameters. Oops, 1 parameters. Okay, you know why? Because we have 3000 W's, W1 until W3000 plus 1B. So these are the parameters. And we're going to find such parameters that this function kind of is learning the binary prediction. Excuse me. But the problem is that any linear mapping has its unbounded range. It could be anything, right? I mean, it doesn't say this will map to 0 or 1. The output could be anything from -infinity to infinity, right? Is it right? Do you see why? Like, it's just a linear function. It could like range from anything. But our examples, our labels are 0 and 1, right? These negative and positives. This is our decision, like 0 and 1. So we have an issue because we want to kind of this function should output 0 and 1, but it's outputting any number. So how can we do that? Can we squeeze it? Can we squeeze, or not squeeze, like can we map somehow arbitrary range into something like which is either 0 or 1? We know okay, nonlinear function. This is interesting. What is nonlinear function? Yeah, linear transformation is the line, so you wouldn't range it, but you need something to make it not a line in a way. And you said, what do you say? Sigmoid function. So what is a sigmoid function? So does it have any properties? Like what do? Okay, so it goes here to 1. Okay, good. And it goes here, which is 0. And at 0, it's right in between. So what's the value here at 0? Oh, okay, interesting. And here it goes like that. Nice little wave. I'm very bad at drawing, but this is the real the sigmoid function. So you were right. So we need to map any number from -infinity to +infinity to 0 and 1. And we have many options actually. It's like the sigmoid function it's fine, but I can also say it's gonna be I can say the function will be if if, let's say z. If z is smaller than 0, then it's gonna be 0, else 1. I'm mapping any number on 0 and 1. Why this is a bad example? This is called step function. Why it's bad? Yeah. Because it has very bad derivative, and exactly the derivative will always be 0 because is it even differentiable? Yeah, in a way. I mean, yeah, it's a stepwise function, and the derivative, so it's going to be like a stepwise function, and the derivative is always 0. Why is derivative 0 a bad thing? Because it doesn't give us any gradient, so we don't know how to learn on this. Okay, so bad idea. This is better. What is the gradient of this function somewhere? I mean, if you look here, if you're far right, the gradient will be also like almost 0, right? And if you're far to the left, the gradient will be also almost 0. But if you're somewhere closer to the middle, the gradient will be some number, positive, 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 smaller. This is great. So this is why it's a interesting function. So the sigmoid function, you should know. You should really know this function. So there's two versions. Typically, this is one we are using. So 1 over 1 plus e to minus t. And what is this derivative? You don't have to know, but you can compute. But if you know, what is the derivative? Wow, respect. So I don't remember this part, actually. I have to look it up, but kudos. Good. But there's a way how to compute this derivative. So why are we interested in derivative? Again, well, we want to plug it into our computational graph, so you need to know how to compute the output. We know exactly how to compute the output. This is this function. And how to compute the derivative with respect to its arguments. So this is t, and this is exactly how we compute this. Like this is the longer part, but then if you do a little bit of algebraic operations, it will end up by saying, oh, this is basically the function itself times 1 minus this function itself. So it's even like fast to compute because you just need to compute this value once, store it, and you're done. You don't have to do all the computation. So it's actually cheap to compute in a way. Okay, interesting. So why is it important? Well, because this function is projecting everything into the whole range, minus infinity plus infinity. Now, if we plug this as an input to this function, it will kind of squeeze to the range between 0 and 1. And this is getting closer to what we really want because we want 0 or 1. Isn't it nice? There could be other functions, by the way. It doesn't have to be only like sigmoid. It could be, what else? Tangents hyperbolicus. H, have you heard of that? It looks something similar. It looks also like that, but I guess that the range is from minus 0.5 to 0.5, and it behaves a little bit differently. But it has to be, oops, come on. It used to be also popular in neural networks, but now sigma is somehow better. Well, so this is it. We have the mapping. And now, finally, we can build this together in a function. So our binary text classification function, awesome. So it's a linear function. Why is it a linear function? Because this is it. This is the linear function. And now we put it into so this is the linear function, and we put it into the sigmoid. So here's the formula of the sigmoid, and voila, we have our log linear model. Why is it log linear model? Because it's linear in the logarithmic space because of the exponentiation, in a way. So, and I build a computational graph here showing that actually we have a couple of nodes here. So this is interesting. This is the input, but the input, it's constant, it's given, right? We have an example, for example, training example or document to classify, so it doesn't change. We cannot do anything with that. It's given. It's a back of words, for example, bunch of numbers. But here are the parameters, so the weights and bias. So this is a vector, this is a scalar, and these are input to this linear node. So this is the projection we are talking about. So we project, and now the question is like, okay, you have a back of words in many dimensions, and we are projecting this into what? So this is a projection into how many dimensions? It's a projection to, we have a 3001, no, 3000, excuse me, 3000. We have 3000 dimensionality, and we're projecting 3000 dimensional space. Can you imagine this? I can't. So I can imagine like 3 dimensionals, 3000, I have no idea. But we have some very complicated space, and we're projecting into some smaller space. What's the space we're projecting here onto? What's the dimensionality of the space we're projecting? I can see you. Yes? It's 1. Exactly. It's to 1 dimension. Basically 2 number. You know why? Like mathematically here, you do the dot product, and dot product is results in a number. And also, if you treat this as a 1-column matrix, the output dimension will be number of columns, which is 1. So you can see it many different ways. We're projecting this onto a number. Okay, this is interesting. So we have this large space. We're projecting onto one real number, which is something from infinity, minus infinity to plus infinity. And then we're squeezing this through the sigmoid, which is squeezing into something between 0 and 1. And then we say, how we make a decision here? That could be interesting. So how can we decide? So we get a number between 0 and 1. How do we say this is positive or negative? How can we say? Yes. We set a threshold, exactly. So we might say, if this is bigger than 0.5, it's going to be positive. And if this is smaller than 0.5, it's going to be negative. This is the typical threshold we're using here. So, okay. So we can now plug in the text, run it through the function, and say, well, this is 0, this is 1. Actually, this model is giving us something very beautiful. The natural interpretation of the output of this sigmoid of the linear projection is a conditional probability of prediction equals to 1 given the input x. So this is the probability that I predicted 1 given x. Of course, I mean, so there is coming a number out of it. For example, the number out of this function will be 0.80. It's possible. It's beyond, you know, after there will be some number, maybe, I don't know, like 3,200.222, and then if you squeeze it through sigmoid, you will get, well, no, this is a bad example. You won't get 0.8. But anyway, let's pretend we got 0.8. So it's saying, well, with probability 80%, this is a positive review. This is the natural interpretation. Like, given the input, the probability that this is positive is 0.8. And the probability it's negative, well, it's 1 minus 0.8. So with probability 0.2, it's the negative review. So it's very nice probabilistic interpretation of the results of this logistic function. Can you take an advantage of that? Well, maybe you can. So sometimes if the classifier is saying, well, it's 99% probability positive, you might trust it more. But I wouldn't rely on that because, you know, the classifier can tell you anything it wants. I'll tell you. I mean, the output of classifier could be anything. It just shows, well, I know in my computations it's very close to, you know, to 1. How you interpret this for your own, like, will you trust it or reject it? It's up to you. But this is the interpretation, like in mathematical terms. Okay, so we have a local linear model. We have the computational graph. How do we? So we can take any vector and we can project it into something between 0 and 1. That's awesome. How do we train this thing? How do we find W and B? Where do they come from? So let's find out. We need to find the best model parameters. Okay, so we talked about losses already. So we know what the loss is. So the loss is the difference between the function output and the gold label. Good. We're going to use one example of loss, which is the binary cross-entropy loss or a logistic loss. And this is it. And I guess you should know it, I guess. Yeah, I guess you should know it. Because it's so central to anything here, then you should really know how to compute this thing, or how to compute logistic loss. I don't think you have to remember somehow the partial derivatives, because, you know, that's not that common. Like, you just program it once and you don't care. But you should know what the cross-entropy loss is doing. So I'm not gonna go into the details why there's entropy here, why it's called cross-entropy. I'm not going in there. But if you look up the previous lectures on YouTube, there is some explanations on that. What does it have to do with entropy of probability distributions? What does it have to do with cross-entropy and KL divergence? Okay, we're not going in there. So KL divergence is somewhere in, there is some more kind of interpretations of this thing. But at the end of the day, this is the formula we're using, and it kind of works. So this is basically saying how well, what is the loss? What is properties of a loss function? What does it have to do? What is the loss function returning? So can it return a negative number? No, no, no. Okay. So we wanted like the loss function is always positive. And what else? As small as possible. So it should be for the training data, it should be as small as possible. So the minimum would be 0, which means we perfectly fit our data. Okay, because which means if you plug here, for example, we have, if our prediction would be 1, excuse me, this is the gold standard. So if this is 1, and if our prediction would be also 1, if you do the math and are not scared of limits, because otherwise the logarithm will break, you will get the loss of 0 if they're matched completely. And of course, you never get y hat 1. Why? Why don't you get y hat 1 in our model? Because of the sigmoid function, you will never reach 1. It's 1 in the limit of somewhere in the outer space. So it will always be closer to 1. So 0.9999 max, which means here it always also be maximum some like 99999. And then you get like very minimal loss, almost 0 loss. Okay, so it will never break. But if you implement this thing, make sure it won't break because you might get, a logarithm of 0, which is a bad thing. Okay, so we have this loss, and it should be positive and as small as possible, and it kind of tells like how far the prediction and the gold standards are far away from each other. Okay, everybody's with me? Sounds great. Now, well, this is what we've seen before. So this is our computational graph, how to get from vectors of input and parameters to a number. And now this is our gold standard label. And here we are plugging the loss. So the loss, for example, is this function, right? Logistic loss has 2 inputs. One is the output of the network, and one is, excuse me, no, the other way around, This is the output of the vector, the prediction, and this is the gold standard label. So this is the gold standard label, this is the input of the prediction, this is the loss. We have a function now, which is computing a loss over one example. Can we minimize it? Yes, of course. This is what we build, why we build all the machinery of gradient-based propagation, backpropagation, gradient-based minimization on computational graph, because we can minimize this function, by finding parameter, by taking gradient of loss with respect to all the W1, with respect to W2, and so on. And the last one will be all the parameters, so loss with respect to B. This is the gradient. And we can compute a gradient now on this graph for any input. Awesome. And if we compute a gradient, we can use this gradient to change the parameters in order to minimize the loss. We take the step opposite to the gradient, which will result in the minimized loss. This is something we talked about last time you remember the Rosenberg function? So we are taking gradient and computing gradient at any point and going a step in the opposite direction. We can do this. This is a function, multiple inputs. We can compute a gradient because we have computational graph. Nothing is preventing us to minimize this function, because everything is differentiable and fits the framework of this backpropagation on a computational graph. So gradient descent and backpropagation. So these are the tools we're using for minimizing this function. Does that make sense? We're building things it's like Lego. We're building, we're stitching things together, which are super simple. We understand them. But then if you stick them together, like, oh yeah, of course I can do this. There's no difference between like doing this on a simple function a plus b times b plus 1 or this. This is the same, doesn't matter. Simple blocks. I know how to compute a gradient for each of the nodes. I can stitch them together. These are just functions. Same. Awesome. And now we already talk about the gradient descent in a way in the banana function, like you take a step and there is this learning rate. So we have an algorithm which we know already. Now we give it a proper name, stochastic gradient descent, which looks super fancy, but you know already everything. So we have a bunch of training data. We have our loss function. So our loss function is this, right? This is our loss function. This is the graph, input, parameters, and something in between. So we have our loss function, we have the function which outputs the prediction. Oh, this is basically, excuse me, this is f(x) theta, very fancy name for function which takes input and parameters, very fancy. So this is it, this is the function. Oops. So this is what I'm getting, and then I'm taking a single, so this is why it's called online stochastic gradient. I'm taking sample training example, so I just pick one. I compute the loss on this example. So what does it mean? I'm gonna do the forward pass and compute basically the value of the loss. And then I'm gonna compute the gradient of the loss with respect to all these parameters. Oh yeah, of course, this is it. This is the gradient I'm going to compute. How I'm going to compute is by just calling recursively back into this graph what is the partial derivative with respect to all these green things. This is the very same as we did like the per hand computation at the beginning of this lecture. The very same procedure. I'm gonna compute the gradient with respect to the arguments. And then I'm gonna change the arguments by taking a step. So this is again, what was that character? Was it eta? Eta. The learning rate. So I'm going to learning rate times the gradient. So this is direction, but I don't want to overshoot. I mean, I can overshoot. I can make it smaller. This is my hyperparameter. Like the learning rate, something I decide. Like I know the direction, but how far I'm going to go. Like tiny little step times the gradient, or very well, it depends. So we saw it in the banana function. Like sometimes you need small, sometimes you need larger. So it's a tricky one. I'm going to update the parameters and run again. So this is basically how we optimize the Rosenberg function, the banana function. This is the very same thing. But now our function is something more fancier, a little bit. So it's a logistic function. And the loss is also something more fancier, which is the cross-entropy loss. But at the end of the day, it's a function which can be differentiated with respect to these to the inputs and the parameters. So this is the one hammer. If there is one algorithm in NLP, there is one algorithm, by the way. This is it. This is one algorithm. This is what you need. This is all you need to do to be rich. Stochastic gradient descent. And to know how to compute backpropagation on the graph. There's no more, I mean, of course, there's a couple of you, like how to build your vocabulary by parse and blah, blah, blah. But this is the algorithm. This is only one algorithm that you're gonna know in here. The rest is just how to stack the computational graph, what are the functions, it could be more complicated and stuff like that. But this is the algorithm. So the point is that the loss here is based on just a single training example, which is kind of tricky. So it doesn't give you a good approximation of the gradient for all training data. So we're gonna do something a little bit better. We're gonna do mini batch stochastic gradient descent, which is, I'm gonna finish in 2 minutes, so no worries. There's 20 slides left. So we're gonna do in each step, we're gonna take m examples. So just a subset of the training data. And then we just iterate over these examples and compute again the loss and the gradient, but we're gonna make an average. It's basically the average gradient. So for each example here, we're computing the loss and its gradient, and then we do it for all the examples in our mini batch, which is a subset of the training data. And then we take the average gradient. So we kind of approximating the value of the gradient for the entire data set, but we're just taking a part of that. Okay? So this is something you should know. But at the same time, it's not much different from what we had in in the Rosenberg function, just a gradient-based optimization in any functions. So the mini-batch stochastic gradient descent, so the mini-batch size can be from 1 to the whole data set. And there's pros and cons. So the higher values of the mini-batch, they get better gradients. And smaller values, they could be faster. And of course, this thing can be parallelized. What does it mean? Because you can compute a gradient for each example in your batch independently of the others. Why is it good to parallelize things? It's faster. It's faster. Oh, what do we say? And on GPU, it's much faster because GPUs are super parallelizable for many reasons. So that's why it works. You can make it parallel. And so what happens on GPU if M is large? So the batch size is large. Like, it depends what large is, but if it's getting large, what issues are you getting into? It's efficient. It's actually better, but you're running out of memory. So basically what you're doing is like to pick the batch as big as possible so you fit your beefy GPU, like A100 with 80 gigs VRAM, if your model is big. What does it mean big? Well, you have so many parameters. I mean, big, we have a 3001 parameters piece of cake. If this is like 70 billion parameters, it's going to be big. You have to fit it. Your function will be big, so you have to fit it in your memory. And you want to do it multiple times, like n times, parallel to each other, or the input will be big as well. Well, it doesn't matter. So you will run out of the memory sooner or later. So you were saying? No. Okay. No. So this is the mini-batch stochastic gradient descent. This can be parallelized, which is great, and let's make it faster. Recap. Tokenization is tricky, but back of words is the simplest baseline. If you ever do some whatever classification, how to turn this text into features? Yeah, back of words, easy. Because for classification it might work. Why? Because in movie reviews, if you see words like "oh crappy" or something positive, beautiful. Oh, the movie is so beautiful, blah 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 blah. Well, you have the word beautiful. And it's enough, maybe, that the overall kind of thing will be positive. It's a good signal. It's not the best one, of course, because ordering of words matter, but it's good enough. Like empirically it works. Back of words is good baseline. We talk about binary classification as a linear function of words and the sigmoid. And we talk about the logistic laws. There could be other losses like squared laws. Squared laws could actually work too. I mean, why not? You can plug in, if you go here, and you plug it here, square laws, why not? It could work. Empirically, it's been shown that for this task, for binary classification, the cross-entropy loss works empirically better for some properties. Maybe there's even like theoretical properties, which I'm not aware of, but rule of thumb, cross-entropy loss is the best choice number one. But you can play around with that. Like everything is kind of how you build it. So we have this loss. And now we had a hammer, optimization hammer, minimizing the loss using mini-batch stochastic gradient descent. And for mini-batch stochastic gradient descent, you need efficient computation of gradients, which is just backpropagation. So you just need to build the computational graph, and it knows how to compute gradient. This is how all the frameworks we're using now work under the hood. PyTorch, TensorFlow, anything else. It's a computational graph, very efficiently built, and very be efficiently parallelized and scaled, if possible, and optimized, and then scale on GPU. That's it. Okay, we made it on time. Thanks a lot. I'll see you in the afternoon.